Molecular orbital theory, the quantum picture of bonding. Molecular orbital theory represents the most complete quantum mechanical description of chemical bonding. Unlike valence bond theory, which pairs atoms into localized bonds, Mo theory treats the entire molecule as a single quantum system. Atomic orbitals combine to form molecular orbitals that extend over the whole molecule. Electrons occupy these molecular orbitals according to the same rules that govern atomic orbitals, the Aufbau principle, Hund's rule, and the Pauli exclusion principle. This framework explains phenomena that simpler theories cannot, including paramagnetism of oxygen, bond order, and the electronic structure of excited states. The wave nature of electrons in molecules. The foundation of molecular orbital theory is the wave nature of electrons. When two atoms approach each other, their atomic orbitals overlap and combine mathematically. Constructive interference produces bonding molecular orbitals with electron density between the nuclei. These are lower in energy than the parent atomic orbitals. Destructive interference produces antibonding molecular orbitals with a node between the nuclei. These are higher in energy. The result is a set of molecular orbitals that describe where electrons in the molecule are likely to be found. Sigma and pi molecular orbitals. Molecular orbitals are classified by their symmetry relative to the internuclear axis. Sigma orbitals are symmetric around the bond axis, formed by head-on overlap of s orbitals or end-on overlap of p orbitals. Pi orbitals have a nodal plane containing the bond axis, formed by sideways overlap of p orbitals. Each type has both bonding and antibonding versions, sigma and sigma star, pi and pi star. Sigma bonds are generally stronger than pi bonds due to greater orbital overlap. Single bonds are sigma bonds. Double bonds consist of 1 sigma plus 1 pi, and triple bonds have 1 sigma plus 2 pi bonds. Bond order from Mo theory. Bond order in molecular orbital theory is calculated as half the difference between the number of electrons in bonding orbitals and the number in antibonding orbitals. Bond order equals bonding electrons minus antibonding electrons, all divided by 2. For H2, with 2 electrons in the sigma bonding orbital, bond order is 1. For He2, with 2 bonding and 2 antibonding, bond order is 0. And indeed, He2 does not exist as a stable molecule. For O2, with 10 bonding and 6 antibonding electrons, bond order is 2, matching the double bond in valence bond theory. Hydrogen is the simplest example of Mo theory. Each hydrogen contributes 1s atomic orbital. They combine to form the bonding sigma 1s orbital and the antibonding sigma 1s star orbital. 2 electrons fill the lower energy sigma 1s orbital with opposite spins. Bond order is 1, a single covalent bond with bond energy 435 kilojoules per mole. H2+ has bond order 0.5, longer bond at 106 picometers, and weaker bond energy at 255 kilojoules per mole. S and p orbital overlap. When an s orbital on one atom overlaps with a p orbital on another, the result is a sigma molecular orbital. The orientation matters. Maximum overlap occurs when the p orbital points directly at the s orbital. This is the geometry of sigma bonds in molecules like HCl, where the hydrogen 1s overlaps with a chlorine 3p orbital pointing toward it. The bonding MO has electron density between the nuclei, lowered in energy. The antibonding sigma star has a node between the nuclei, raised in energy. Strong sigma bonds require good orbital overlap. sp mixing and orbital reordering. In diatomic molecules of the second period, an interesting effect occurs. Sigma 2s and sigma 2p orbitals can mix, changing the energy ordering. For elements Li2 through N2, the sigma 2p orbital is higher in energy than the pi 2p orbitals. For O2, F2, and Ne2, normal ordering is restored. This reordering, called sp mixing, affects the magnetic properties of O2 and the bond strengths across the period. It arises from the interaction between orbitals of similar symmetry on neighboring atoms and is a key concept in Mo theory. Paramagnetism of oxygen. One of the great triumphs of molecular orbital theory is explaining why O2 is paramagnetic. Lewis structures suggest all electrons in O2 are paired, which would predict diamagnetism. But MO theory correctly predicts paramagnetism. The MO diagram of O2 shows 12 valence electrons. The last two electrons occupy the two degenerate pi-star antibonding orbitals singly, with parallel spins, following Hund's rule. These two unpaired electrons make O2 paramagnetic. It is attracted to magnetic fields. This was a famous failure of valence bond theory that MO theory resolved. Heteronuclear diatomic molecules. When the two atoms in a diatomic molecule are different, the MO diagram becomes asymmetric. The more electronegative atom has lower energy atomic orbitals. For HF, the fluorine 2p orbitals are much lower in energy than the hydrogen ones. Electrons in bonding orbitals spend more time near fluorine, contributing to the molecule's polarity. Carbon monoxide CO is a particularly important heteronuclear diatomic. Its MO diagram reveals why it has a triple bond despite the formal charge separation. No, nitric oxide is a radical with 11 valence electrons and a bond order of 2.5. Conjugated pi systems and delocalization. When molecules have alternating single and double bonds, the p orbitals on adjacent atoms can overlap sideways, creating an extended pi system. This is conjugation. In butadiene, the 4p orbitals combine to form 4pi molecular orbitals, with electrons delocalized over the entire pi system. Conjugated systems have unique properties: lower energy than predicted by localized bonds, longer wavelength absorption of light, and distinctive reactivity patterns. The delocalization energy, or resonance energy, makes conjugated molecules more stable than their localized counterparts. This is the foundation of organic chemistry. Mo theory in organic molecules. The HOMO-LUMO gap determines a molecule's color and reactivity. The highest occupied molecular orbital, or HOMO, is where electrons come from in reactions. The lowest unoccupied molecular orbital, or LUMO, is where electrons go. A small HOMO-LUMO gap means the molecule absorbs visible light. This is why conjugated dyes are colored. The Woodward-Hoffman rules use molecular orbital symmetry to predict whether paracyclic reactions are allowed under thermal or photochemical conditions. This was a major triumph of MO theory in the 1960s. Mo theory for polyatomic molecules. For molecules with 3 or more atoms, MO theory uses symmetry-adapted linear combinations, or SALCs, of atomic orbitals. Group theory classifies the molecular orbitals by their symmetry species. For water, H2O, the central oxygen's 2s and 2p orbitals combine with hydrogen 1's orbitals to form 4 molecular orbitals, 2 bonding and 2 antibonding. The 8 valence electrons fill the 2 bonding orbitals. The non-bonding lone pairs on oxygen are essentially the original oxygen 2p orbitals perpendicular to the molecular plane. This is why water has a bent geometry. Mo theory is essential for transition metal complexes, where crystal field theory provides only a partial picture. In an octahedral complex, the metal 3d, 4s, and 4p orbitals interact with ligand sigma donor orbitals to form a complete MO scheme. The metal T2g orbitals are non-bonding in sigma-only bonding, while the Eg orbitals form sigma bonds. Mo theory also accounts for pi bonding. Ligands like CO, Cn-, and phosphines accept electron density from the metal into empty pi-star orbitals, called pi backbonding. This explains the spectrochemical series and why CO is a strong field ligand, while I- is a weak field ligand. Mo theory is directly supported by experimental evidence, especially photoelectron spectroscopy, or PEES. PES measures ionization energies of electrons in molecules by irradiating them with high-energy photons. The spectrum shows peaks for each molecular orbital energy level, with peak heights proportional to electron count. For N2, PES shows peaks at 15.6 electron volts for sigma 2s, 16.7 electron volts for sigma 2 star, 18.8 electron volts for pi 2p, and 37.3 electron volts for sigma 1's core. For O2, PES confirms unpaired electrons through peak fine structure. The agreement between theory and experiment is remarkable. Question: According to molecular orbital theory, what is the bond order of N2? Options: A, 1, B, 2, C, 3, D, 4. Question: why is O2 paramagnetic? Options: A, it has unpaired electrons in pi star orbitals. B, it is a metal. C, it contains iron impurities. D, it has a permanent dipole moment. Question: which molecular orbital has a node between the two nuclei? Options: A, sigma bonding orbital. B, pi bonding orbital. C, sigma star antibonding orbital. D, all bonding orbitals. Question: the bond order of O2 calculated from MO theory is options: A, 1, B, 1.5, C, 2, D, 2.5. Question: why is He2 not a stable molecule? Options: A, helium is a noble gas. B, bond order from MO theory is 0. C, the atoms repel each other. D, it would violate the octet rule. Problem. Using molecular orbital theory, determine the bond order of O2 and predict its magnetic properties. Solution. O2 has 12 valence electrons. Fill the MO diagram. Sigma 2s, sigma star 2s, sigma 2p, 2 pi, 2p, then 2 pi star 2p. The last 6 electrons fill. 2 in pi 2p, 4 total, then 2 in pi star 2p with parallel spins. Bonding electrons, 8. Antibonding electrons, 4. Bond order, 8 minus 4 divided by 2 equals 2. 2 unpaired electrons in pi star orbitals make O2 paramagnetic. Problem. Calculate the bond order of no plus and no mines from molecular orbital theory and predict their stability relative to no. Solution. No has 11 valence electrons with bond order 2.5. No plus has 10 valence electrons, removing one antibonding electron, so bond order increases to 3. No has 12 valence electrons, adding one antibonding electron, so bond order decreases to 2. Therefore, no plus is more stable than no, which is more stable than no. This is observed experimentally. No plus forms stable salts like no plus Bf4 minus, while no is rarely observed. Problem. Predict whether C2 is best described as having a double bond based on MO theory. Solution. C2 has 12 valence electrons. Fill the MO diagram. Sigma 2s, sigma star 2s, then pi 2p, pi minus 2p, sigma 2p. The last 4 electrons fill the 2 pi 2p orbitals. Bonding electrons, 8. Antibonding electrons, 4. Bond order, 2. However, the bond is a double pi bond, not the typical sigma plus pi double bond. C2 is therefore a doubly bonded molecule, but its bonding pattern is unusual, a textbook example of MO theory giving a different answer than valence bond theory. Problem. Compare the bond orders and bond lengths of N2, N2+, and N2-. Which is most stable? Solution. N2 has 10 valence electrons, bond order 3, the strongest. N2+ has 9 valence electrons, removing 1 bonding electron, bond order 2.5, longer and weaker. N2 has 11 valence electrons, adding 1 antibonding electron, bond order 2.5, also longer and weaker. Both ions have bond order 2.5, but N2+ is generally more stable because removing an electron from a high-energy orbital is easier than adding to a low-energy one. N2+ is observed in mass spectrometry. N2 is rare. Problem 5. Using Huckel-Moe theory, determine the pi-MO energy levels for benzene C6H6. How many pi-MOs are bonding and how many are antibonding? What is the total pi-electron stabilization energy relative to a hypothetical localized structure with 3 isolated double bonds? Benzene has 6 carbon atoms in a ring, each with 1,2 pz orbital. 6 atomic orbitals combine to form 6 pi-MOs. Huckel formula. EK equals alpha plus 2 beta times cosine of 2 pi k divided by n. For k equals 0, E equals alpha plus 2 beta, the lowest energy, fully bonding. For k equals plus or minus 1, E equals alpha plus beta, bonding, degenerate. For k equals plus or minus 2, E equals alpha minus beta, antibonding, degenerate. For k equals 3, E equals alpha minus 2 beta, the highest, most antibonding. 3 bonding MOs at energies alpha plus 2 beta, alpha plus beta, and alpha plus beta. 3 antibonding MOs at energies alpha minus beta, and alpha minus 2 beta. 6 pi electrons fill 3 bonding MOs. Total pi energy is 2 times alpha plus 2 beta plus 4 times alpha plus beta, which equals 6 alpha plus 8 beta. A localized structure of 3 ethenes has each ethene with 2 pi electrons at alpha plus beta for a total of 6 alpha plus 6 beta. The delocalization energy is the difference. 6 alpha plus 8 beta minus 6 alpha minus 6 beta equals 2 beta. Since beta is negative, the actual delocalization energy equals 2 times the absolute value of beta, approximately 150 kilojoules per mole. This aromatic stabilization is why benzene is unusually stable and aromatic. Let us review the key concepts from this lesson on molecular orbital theory. Core principle. Atomic orbitals combine via LCAO to form molecular orbitals. The number of MOs formed equals the number of atomic orbitals that combine. Bonding MOs are lower in energy, while antibonding MOs are higher. Bond order. Bond order equals the number of bonding electrons minus the number of antibonding electrons, all divided by 2. Bond order 1 means single bond, 2 means double, 3 means triple. Fractional bond orders are possible. Sigma and pi orbitals. Sigma MOs come from end-on overlap with no nodal plane through the nuclei. Pi MOs come from side-by-side overlap with one nodal plane containing the internuclear axis. Sigma bonds are stronger than pi bonds. SP mixing. For Li2 through C2, SP mixing causes sigma 2p to be higher in energy than pi 2p. This explains B2's paramagnetism and C2's unusual bonding. Heteronuclear MOs. Different atomic energies yield asymmetric MOs. Bonding MOs have more character from the more electronegative atom. CO, NO, and HF are key examples with distinct properties. Molecular orbital theory stands as one of the greatest intellectual achievements of 20th century chemistry. From the simple hydrogen-1s orbitals to the complex pi systems of DNA base pairs, from the paramagnetism of oxygen to the triple bond of nitrogen, from the aromatic stability of benzene to the radical reactivity of nitric oxide, MO theory provides a unified, quantum, mechanically rigorous framework for understanding chemical bonding. It explains why some molecules form and others do not. It predicts magnetic properties that no other theory could anticipate. It reveals the electronic origins of color, conductivity, and chemical reactivity. And it provides the theoretical foundation for modern materials science, from organic semiconductors to transition metal catalysts. The wave-like nature of electrons, their constructive and destructive interference, and the elegant mathematics of orbital combination. This is the language in which the universe writes its chemical rules. Understanding MO theory is not just learning chemistry, it is learning to think like a quantum